All right, today we're going to go ahead and hit section 6.2, which is we're going to deal with the idea of rationals. If I do my job right, hopefully you'll see the connection between what we did yesterday, which is with radicals, rooting, some fractional exponents. This is hopefully just going to build off what you already know. Also, we're going to combine some things. Basically, the idea of what we did yesterday, which is fractional exponents on the right-hand side, and something that we talked about in the last chapter with polynomial expressions. On the left-hand side here, remember that when we are multiplying exponents, we keep the base the same and we add them. When we are raising exponents to a power, we multiply them and keep the base the same. We distribute them in when we have multiple terms there. My reminder to you guys, hey, remember there's always an exponent of 1. Fractional exponent, a negative exponent means it's in the wrong spot. Division means subtraction. Make sure when we're raising to an exponent, we distribute to both the numerator and the denominator. Well, our rules for exponents will stay exactly the same. Today, we're going to apply the rules, but we're going to apply them to our fractional exponents. So the only thing that you guys are probably not going to like is the fractions part of it, because I think most of you guys are pretty good with the actual rules, that stuff on the left-hand side. So let's see how they look. Simplifying, reviewing our rules, make sure we're okay with that before we move forward. First off, 7 to the 1/4 times 7 to the 1/2. My base is the same here. So that means when I am multiplying exponents with like bases, my base will stay the same, and multiplication means addition. So that's going to be 1/4 plus 1/2. 7 to the 1/4 plus 1/2. You guys have to do a little bit of fraction work there. That is going to be 7 to the 1/4 plus, I'm going to change 1/2 to 2/4, finding a common denominator there. 1/4 plus 2/4, that gives me 7 to the 3/4. Today, we don't have to simplify those down. I'm not going to make you do that. You can leave your answers just as fractional exponents. So 7 to the 3/4 is fine. I'm more concerned that you understand how these rules work. Next up, 6 to the 1/2 times 4 to the 1/3, all raised to the second exponent, or or squared. Realize here we're raising the exponents. That means we will distribute this into both terms, and that's going to give us, I'm going to write down here, that's going to be 6 to the 1/2 times 2 to the 1. There's my distribution for that one. My next one is going to be 4 to the 1/3 times 2 over 1. Simplify this a little bit. Hopefully you can see that 6 to the 1/2 times 2 over 1. Your 2's will cancel. That will be 6 to the 1. So I'm just going to leave that as 6 times 4 to the 2/3. 1/3 times 2 over 1. I cannot combine the 6 and the 4 at this point. 6 and the 4 are not like terms. They have different bases, so I will have to leave them there. That's actually exactly how I leave my answer. 6 times 4 to the 2/3. Next up, four to the 5th times 3 to the 5th raised to the negative 1/5. Couple things. We've got a negative fractional exponent. I'm going to take care of that and distribute it in first. That's the way I like to take care of it. So that's going to be 4 to the 5 over 1, or 4 to the 5th, times the negative 1/5. That's distributing to the first term. Base stays the same. I multiply the exponents. I'll be multiplying that 3 to the 5 over 1 times the negative 1/5. Again, distributing that all the way in. Hopefully you'll see that these cancel. That'll give me a 4 to the negative 1. 5 over 1 times negative 1/5 times 3 to the negative 1 also. Now, things got a little bit easier. I got rid of my fractions there. 4 to the negative 1 times 3 to the negative 1. I like that. Again, I know that fractional exponents means that term is in the wrong part of my fraction. So that means 4 to the negative 1 does not belong in the numerator. It needs to move down to the denominator. When I move it down, I make that exponent positive. Also, 3 to the negative 1 is in the wrong location. I'll move him down. I do need a placeholder up top because I have nothing actually up there anymore in the numerator. That's 1 over 4 times 3. So this answer will simplify to 1/12. Okay? Rules of exponents with some fraction work here. It's really what this is. Letter D. 5 to the 1/3. 5 divided by 5 to the 1/3. This is division of exponents. 5, hopefully you'll agree when I rewrite this. That's the same thing as saying 5 to the 1. 5 is 5 to the 1 divided by 5 to the 1/3. Division of exponents means subtraction. If I'm going to subtract fractions, I need to have a common denominator. For me, it's an easy one. Another way to write 1. I told you the number 1 is going to show up many times in this class. I'm going to choose to write 1 as 3 over 3. The reason I'm choosing 3 over 3 is because I need to have a common denominator, and I'm going to be subtracting those exponents. So, base stays the same. That's going to say 5 to the 3/3 over 5 to the 1/3. That means 5 to the 3/3 minus 1/3. Division is subtraction. So that gives you 5 to the 2/3 exponent. Negative 2/3. Sorry about that. Oh, no, actually, 5 2/3. We're good. That's all you have to do for that one. Division means subtraction. Lastly, letter E here. We're going to distribute that 2 into both terms. That's 42 to the 1/3 over 6 to the 1/3 squared. So the first thing I'm going to do is to distribute the 2 both to the numerator and the denominator. So that's going to say 42 to the 1/3 times 2 over 1 divided by 6 to the 1/3 times 2 over 1. Next thing I'm going to do, simplify those out. That is going to be 42 to the 2/3 over 6 to the 2/3. And now I want to tell you about one unique rule. This one's kind of tricky for students. I have the exact same exponent as 2/3 here. When that exponent is exactly the same, I actually can reduce that fraction. I can do the math that it's asking me to do. 42 divided by 6 is 7, or 6 goes into 6 once, 6 goes into 7, 6 goes into 42 7 times. That answer would be 7 to the 2/3 over 1 to the 2/3. 1 to the 2/3 is just 1. So this answer is going to be 7 to the 2/3. Again, this is tricky. The rest of the ones you guys have seen before, they make sense because they're all the same rules applied that you've seen, just some fractions instead of whole numbers. Negatives are still there. This distribution is still there. The only tricky thing is when you have the exponents the same, you can actually reduce your fraction within it. So it's kind of a weird, quirky little rule. Shows up once in a while. You can do that problem the long way. It just takes more time. So only when those exponents are the same can you do what I just did. But if you do recognize that, it's a nice time saver. All right. Next up. A mammal's surface area in square centimeters can be approximated by the model S equals K m to the 2/3, where m is the mass of the mammal and K is a constant. The values of K for some mammals are shown below. The approximate surface area of a rabbit has a mass of 3.4 kilograms. There's 3.4 times 10 to the 3rd. That's what we need to do. So it's asking us to find the surface area. You guys are probably getting the patterning on these word problems, by the way. Surface area, they gave us an equation. We got to plug the right things in the right place. So we're looking for surface area, so we're not going to plug anything in for S. We know that our equation is S equals K M to the 2/3. Obviously, we've got some fractional exponents. We've kind of been dealing with that the whole time. It says K is a constant. For mammals, we're talking about a rabbit in this case. So that means our constant, which is K, must be the constant for the rabbit. So that takes care of my value for K. Again, we're solving for the surface area. K is 9.75. Next up. It gives me the mass of a rabbit, 3.4 kilograms, which is 3.4 times 10 to the third grams. They gave me that. They gave me that conversion. Because this equation is in grams, so I need to use the in grams part. So my mass is going to be 3.4 times 10 to the third. And remember, my mass was raised to the 2/3 exponent. Now, this is just fractional exponents, rules of exponents with the calculator. That's really what we're doing here. There's our equation. Hopefully it makes sense as to where I'm finding it from. Mass, I'm substituting in for M. K is my constant for the rabbit, and I'm looking for my surface area. Let's calculate or crunch this. S equals 9.75. I'm going to distribute that 2/3 in. Remember, this is to parentheses. Reminder that that exponent is 1 there. Distribute this to both terms. So that's going to be 3.4 to the 2/3. That's 1 times 2/3 times 10. That is 3/1 times 2/3 are 2. So your 3's will cancel, give you 2/1 or 10 squared. At this point, to get my surface area, it's going to be 9.75 times 3.4 to the 2/3 times 10 squared. I'm going to write that as 3.4 to the 2/3 times 10 squared, by the way, is 100. And 100 times 9.75, I'm just doing a little bit of work here. 100 times 9.75, I'm going to move that decimal over twice, so that's going to give me 975. That's 9.75 times 100. I'm going to need to multiply that by 3.4 to the 2/3. At this point, I'm ready to go to my calculator. 3.4 to the 2/3, we talked about how to calculate that yesterday. 3.4 raised, parentheses, 2 divided by 3. Close the parentheses, enter, and that'll give us 3.4 to the 2/3. That beast of a decimal. We need to multiply that value, 3.4 to the 2/3 times 975, in order to get our estimate of surface area. So I'm just going to hit times. Remember, that's going to plug in my answer automatically. Times 975. And wham, bam, thank you, ma'am. It's about 2,204.57. So we'll write that. Remember to write your approximation. So we're going to say approximately 2204 point, I can't remember what that decimal was, 57. And that's my surface area. Surface area is going to be in different units on surface area. We've got centimeters or something like that. Probably. Square centimeters area. So centimeters squared. Okay. Make sure you're using those approximation marks because that means about. It's not exactly. Plug, chug, calculator, crunch there. Make sure you get the right values in the right locations. That'll be you guys. We're going to crank through some simplifying here. I'm not going to spend a lot of time on that. I'm going to actually work the examples. Rules of radicals, rules of fractional exponents. That's really what we're looking at here. First part, letter A, cube root of 12 times the cube root of 18 can be written just like we could write things before. We can combine that, and that's what I'm going to do here. That's the cube root of 12 times 18. You could multiply that together if you want. I wouldn't, because as soon as you multiply that together, I'm going to tell you to make a factor tree. Again, cube root, we broke these down yesterday. Let's get things up 3. That's what we're looking for here. That's a 6 times 2. I notice that this 18 is a 6 times 3. Something that makes sense to me right now is realizing if I look at this problem, I know the cube root of 12 times 18 is actually going to be 6. And maybe pause the video and try to see why I got 6 right away right there. And I'll finish it up another way too. But there is a way that I can look at that and know that that answer is going to be 6. Next up, if you didn't see how I got that 6 right away, go ahead and factor down those 6s. Remember, you need 3 of something to pull it out. I have 1, 2, 3 2s, so there's a 2 that I'm going to pull out. Again, I need 3 of something to pull it out. There's 1, 2, 3 3s. 1 3 goes out. Nothing is left on the inside. On the outside, I have 2 times 3, which is indeed 6. So, cube root of 12 times cube root of 18 simplifies to 6. Next up, that 4th root of 80 times the 4th root of 5. What I do, and I think it makes it a little bit easier, just like I did in part A, I'm going to write this under one root. The 4th root of 80 over 5. Gee, I like that a lot because 80 over 5 I see as a fraction. Mr. Wood always makes me reduce my fractions. Therefore, I think it might be a good idea if I reduce this fraction so I have smaller numbers. I notice that 80 and 5 are multiples. 5 goes into 5 once. 5 goes into 80. I don't know how many times. 36. I think that's right. And that'd be 36 over 1. Let me double check that. 4th root of 36 over 1. By the way, the 4th root of 1 is going to be just, oops, it's 16, not 36. 16 over 1. How about if I reduce my fractions correctly? And that's going to give me now the 4th root of 16 over the 4th root of 1. By the way, the 4th root of 1 is just 1. My denominator is 1, so I'm really concerned with just the 4th root of 16. A lot of you guys already know the answer to the 4th root of 16. It's going to be 2. If you want to factor that down, 4 and 4, 2, 2, 2, 2. 4 of something, 1, 2, 3, 4. I'm going quick on that because I think you guys are comfortable with it. Okay? Apply and use what you know. The rules of exponents stay the same, whether they're fractions, whether they're negatives. It's just the same rules of exponents over and over and over again. Part A, write the expression in its simplest form here. That's pretty straightforward. You just need to write it. We need to simplify it, just like we do with the other radicals. Cube root of 135. Remember, we need 3 of something. That's going to be 5 times, let's see, 10, 5 times 25. And how about 5 times 27? Ooh, my mental math is not doing well today. 5 times 27. 27 I can break down as to 3 times 9. And my 9 is 3 times 3. Remember, I need 3 of something to pull it out. There's 1, 2, 3 3s. This 5 is now stuck on the inside. It's going to be 3 cube root of 5. It's the first time we haven't seen something that's a perfect cube. It's just like we do with square roots. Not a big difference there. Just a cube root instead of a square root. Letter B, we're going to skip. You don't have to worry about that. So I'm just concerned that you can break it down like letter A. Don't worry about letter B. Simplify. Best thing I can tell you here on simplifying is look for like terms. Like terms are things that are alike. Fourth root of 10 is the same as the fourth root of 10. Big deal in combining like terms. Think back to the last chapter. When I had 3x cubed and 2x cubed, I added that together to get 5x cubed. I kept the like term the same and I combined the coefficients. You guys have been combining like terms forever. This really screws up students, even though it's a very easy thing. Like terms stay alike. And you do the operation on the outside. In this case, that is the fourth root of 10 plus 7 fourth root of 10. The answer is going to be 8 fourth root of 10. The like term stays the same, and you do what it asks you to do, 7 plus 1. Letter B, 2 times the 8 to the 1/5 plus 10 times 8 to the 1/5. The 8 to the 1/5 is the like term. It will stay the same. And you do what it tells you to do. 2 plus 10 is 12. So that will be 12 times the 8th root of 1 to the 5th. Keep the like terms the same and do what it tells you to do. But Mr. Wood, the cube root of 54 is not the same as the cube root of 2. I can't combine them. I know you can't combine them. You're not supposed to yet. In fact, what am I going to tell you to do with the cube root of 54? Hopefully you said, break it down to the video just now. Cube root of 54, we'll break down. I'm going to write that as, let's see, 27 times 2, 9 times 3, 3 times 3. You need 3 of something in this case to pull it out. So hopefully you'll agree that the cube root of 54 simplifies to 3 cube roots of 2. Remember that 2 is still on the inside. And I will be subtracting the cube root of 2. 3 cube roots of 2 minus the cube root of 2. Realize that these are like terms. There's a number 1 sitting out in front there, just like there was a number 1 sitting out in front on letter A. That's going to say 3 cube root of 2 minus 1 cube root of 2. So that answer is going to be 2 cube roots of 2. Combine like terms. Combine like terms. Do what it tells you to do and keep the like term the same. I think that's one of the easiest things you're going to do. Students just kind of really get confused over what to do in what place. You're going to see that again on the next example. So this is not a night to shortchange your homework, because I'm going to expect that you can manipulate all these things together. It is a kind of one of those attention to detail things. I would definitely encourage you guys to start making index cards. If you're somebody that doesn't gets confused kind of easily with math, I would make index cards. Let me find it on here. Of this thing right here. Make an index card. Number 1 would be an index card with an example on one side and the generic rule on one side. Number 2 would be in its own. Number 3, number 4, number 5, number 6. So you understand what the rules do. That is what I would kind of memorize to make sure you're okay with getting things in the right place and doing the right thing at the right time. Because honestly, that's the hardest part. Doing the right thing at the right time. That'll be you guys to work on. Next up, as I said, things are going to get kind of tricky here. Take your time, get it right. Cube root of 64, y to the 6th. Break down 64. 64, I'm going to break down to as 32 times 2. I'm going to break down 32 as 16 times 2. And then I'm going to break that down to 8 times 2, 4 times 2, and 2 times 2. I need 3 of something to take it out. I've got 1, 2, 3 2's. I'm taking 1, 2 out. 1, 2, 3 2's. I'm taking another 2 outside. I have nothing left of that 64 on the inside of that radical. So I still have the cube root of y to the 6th that I have to simplify. 2 on the outside, cube root of y to the 6th. Looking at y to the 6th right now, you will have to factor tree the y to the 6th. Remember, you need 3 of something. Exponents. Your rules for exponents is that you actually add them and keep the base the same. We talked about that earlier today. I need 3 of something in order to take one of those y's outside. Hopefully this makes sense to you. I can break down in a factor tree y to the 6th as y squared times y squared times y squared. Because 2 plus 2 plus 2 is y to the 6th. If I multiplied, and you can't see it right now, but if I covered up y to the 6th, and I told you to combine y squared times y squared times y squared, you should say that that's going to go to y to the 6th. Then it should make sense to you that y to the 6th will break down to y squared times y squared times y squared. A very helpful thing when we're looking at the variables here, makes sense to me, is this. 3 goes into 6 how many times? Hopefully you said 2. That means I can break that into y squared times y squared times y squared. Again, 3 goes into 6 twice. That's how I'm going to factor tree that. Y squared times y squared times y squared. This is a perfect root. I have 3y squareds. I will have a y squared outside. Remember, I was going cube root of 64y to the 6th. Hopefully, you see that the cube root of 64y to the 6th is going to be 4y squared. The 4 comes from my 64. The y squared comes from the cube root of y to the 6th. There is some patterning here. As we work through the additional examples, you're going to kind of see how the patterning works. (27p cubed, q to the 12, raised to the 1/3. Hopefully you're recognizing, hey, I'm going to distribute that 1/3 in. I will remind you, make sure you remember to distribute it into all terms. Students forget the 27 part. That's a 27 to the 1. So that will be 27 to the 1/3. That's going to be p cubed raised to the 1/3, or 3 over 1 times 1/3. And that's going to be q to the 12 over 1 raised to the 1/3. Remember, we distribute that in. You're going to see some things happening with fractional exponents. That should match with your rules of exponents. Some of you guys actually already recognize that 27 is a perfect cube. You also recognize in a fractional exponent that's saying the cube root of 27. Those two things say exactly the same thing. Cube root of 27, 9 times 3, 3 times 3 times 3, 27 to the 1/3, or cube root of 27, simplifies to 3. Next up, looking at my p, that's 3 over 1 times 1/3. 3 over 1 times 1/3, that's just going to be p to the 1. I'm not going to put an exponent on that. Hopefully you agree. Q to the 12 over 1 times 1/3 is 12 over 3. So that's going to be 3p q to the 4. That's actually my answer to this problem. That is one way to solve this problem, distributing and taking fractional exponents. The other way to look at this problem, and this probably makes more sense to you guys right now, I'm going to make this whole thing the cube root. If I make that whole thing the cube root, I still have 27, p to the 3rd, q to the 12th. Remember, those say the same thing. Notice that I'm going to get the same answer here. The cube root of 27, that's 9 times 3, 3 times 3 times 3. From the 27, I will take out a 3. Hopefully you remember that division trick I did on that last problem. 3 goes into 3. I'm going to split that as P1 times P1 times P1. That's going to factor tree that down. I need 3 of something to take it out. There's my P. 3 goes into that 12 exponent 4 times. So that factor tree should make sense to you as Q to the 4, Q to the 4 times Q to the 4. Again, I need 3 of something to pull it out. There's my Q to the 4. Both answers exactly the same. Oh me, oh my. I'm shocked that fractional exponents go hand in hand with radicals. They're connected. They're saying the same thing. See the relationship. All right, Mr. Wood, I got this. Give me something hard. This one's not that bad. Neither one of these are that bad. This is the 4th root of n to the 4th, and the 4th root of n to the 8th. We've got to simplify this. Easiest way to simplify this is to break it into 2 fractions. It's going to be the 4th root of n to the 4th up top over the 4th root of n to the 8th on the bottom. 4th root of n to the 4th. Some of you guys are seeing this patterning already. I'm going to write that as m. I can do that one in my head. Also, that bottom one, I'm going to tell you, does simplify to n squared. Hopefully, you're starting to see the patterning on that. By the way, that's it, m over n squared. You thought it was hard. I tricked you. 4th root of m to the 4th. 4 goes into 4 one time, which means, in this case, I'll break it down as m to the 1 times m to the 1 times m to the 1 times m to the 1. I'm dividing to figure out what I need 4 of to get one of those things outside. If I'm looking at the 4th root of n to the 8, 4 goes into 8 twice, so that means I'm going to factor tree that down into n squared times n squared times n squared times n squared. Now I have 4 of that to take outside. So hopefully you'll see how I'm breaking that down. That division works good for those exponents. Whew. All right. Letter D. I thought you said this stuff was hard, Mr. Wood. It's not. But this looks hard. There's fractions. Oh me, oh my. No big deal. All we have to do is reduce this fraction. Really simplifying, simplifying. 2 goes into 14. I've got a number and a number. Let's just reduce that. 2 goes into 2 once. 2 goes into 14 7 times. Next, I'm going to deal with my x's. I've got an x up top and an x to the 3/4 down here. I have division of exponents, so I know that my rule is to subtract. My rule is to subtract. That is an exponent of x to the 1. I told you don't forget about that x to the 1. If that's x to the 1, I'm going to write that as 4 over 4. Lastly, I'm going to come back and take care of those x's. I don't have to worry about that y to the 1/3. There's no y in the denominator for that, so I'm going to leave the y to the 1/3 alone. And my z to the -6, that is a negative exponent. It's in the wrong part of the fraction, which means I've got to move that up. Z to the +6. I'm actually almost done with this problem. 7's done. X to the 4/4 minus x to the 3/4. That's really 4/4 minus 3/4. So that is going to be x to the 1/4. Again, how do I get that x to the 1/4? That is 4/4 minus 3/4. Division is subtraction. I changed my x to the 1 to 4/4. That's the special one, just another way of writing it, so I have a like denominator. Y to the 1/3 doesn't change. Z to the 6th didn't change. That is my answer. Lather, rinse, repeat. Almost done here. Simplifying. That's the 5th root of 4, a to the 8th, b to the 14th, c to the 5th. Got to break it down. Remember, in this problem, we need 5 of something to take it out. Well, 4 only breaks down to 2 and 2, Mr. Wood. I don't have 5 of anything. What do? I haven't had that happen before. No big deal. If you can't take a root out, leave it on the inside. Oh, we've done that before. Yes, I know. It's the same thing. Well, how about this a to the 8th? I recognize you told me to divide the 5 into 8. Well, Mr. Wood, the 5 goes into 8. That only goes in once. So I split it down to, and hopefully this makes sense, a times 1, a to the 1, a to the 1, a to the 1, a to the 1. There's 1, 2, 3, 4, 5. Because 5 goes into 8 once. But Mr. Wood, there's a remainder here. Yes, there is. What is your remainder? Well, let's see. 5 goes into 8 once with a remainder of 3. That means I can write a to the 8 the way that I've just written it on the board. 1, 2, 3, 4, 5. Those guys will come out. Here is an a that I'm bringing out. My remainder, the stuff that didn't divide out evenly, needs to stay on the inside, just like my 4 stayed on the inside. That almost makes sense. That's scary. Well, what about the b to the 14th? How's that going to work? Well, I'm going to ask you, how many times does 5 go into 14? Hopefully you just said to your computer, it goes in twice. So that's, I'm going to write b to the 14th in terms of a factor tree. That's going to be b squared times b squared times b squared. Oops, didn't write that one right. Times b squared, 1, 2, 3, 4, times b squared. There's my 5 into 14. Goes twice. And what's my remainder? That's 2, 4, 6, 8, 10. I have a remainder of 4. That must mean I'm taking a 1, 2, 3, 4, 5. I need 5 of something to take it out. I'm taking a b squared out, and I'm leaving a b to the 4th on the inside. Oh, Mr. Wood, I'm starting to see the pattern in here. You mean to tell me when I divide the 5 into the c to the 5th, that goes in once, so that's going to give me a c to the 1 on the outside with no c's left on the inside. Because c to the 5th, I can break down to is to c to the 1 times 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 c to the 1. That's 1, 2, 3, 4, 5 with nothing left on the inside. The division trick works real nice. We just have remainders now, and we didn't have remainders before. So the answer to that rainbow of a problem is ab squared c on the outside, and then the 5th root of 4a cubed b to the 4th on the inside. Not so bad. Just divide it in. Next up, cube root of x over the cube root of y to the 8 is how I'm going to simplify that one. And I'm going to tell you we don't have to do that one. We're skipping it. Don't worry about it. Last bit of problems. I think this is the last example. This one's the easiest stuff that we've done all day. It doesn't look easy, Mr. Wood. It is. We've got like terms again. Cube, square root of w, 1/5 square root of w plus 3/5 square root of w. Keep the like term the same and do what it tells you to do. 1/5 plus 3/5 is 4/5 square root of w. I've got 3xy to the 1/4 minus 8xy to the 1/4. I notice that xy to the 1/4 is exactly the same thing. Well, if it's exactly the same thing, don't I keep that thing the same and do what it tells me to do? So that's going to be 3 minus 8, which is negative 5. Xy to the 1/4. That's all I have to do. Done. But Mr. Wood, 12 cube root of 2z to the 5th minus z cube root of 54z squared is not the same thing. Uh-huh. Well, what should you do to make it look like the same thing? I bet I can break down something here. But it doesn't look, I can't do anything to the 2, Mr. Wood. I know. But you can break down the z to the 5th with our rules of division. 3 goes into 5 how many times? 12. Let's see. 3 goes into 5. That will give me a z squared on the outside with a cube root of 2z cubed on the inside. Did I do that right? No, I did not. That was horrible. 3 goes into 5 once, so that'll bring a z to the 1 outside, and I have a z squared on the inside. Again, z to the 5th, cube root z to the 5th. We're going to break that down to z to the 1 times z to the 1 times z to the 1. 3 goes into 5 once, with a remainder of z squared, or a remainder of 2. I've broken down that left-hand side. Great. Now I need to look at the right-hand side. That says minus z. I already got a z out there. Cube root of 54z squared. I can't do anything with the z squared, but I can break down that 54. That 54 I can break down to, let's see, 2 times, what do we got there? 2 goes into that, 27. 27 is going to be 9 times 3, and 9 is going to be 3 times 3. I have 1, 2, 3 3s. That means I take a 3 out, gives me 3z on the outside, and hopefully you'll agree, I couldn't do anything with that z squared. So this whole expression, when I simplified and simplified, says 12z cube root of 2z squared minus 3z cube root of 2z squared. Remember, I had that 2 there. Mr. Wood, you guys coming back in? Hopefully you guys are coming in. All we have to do is combine like terms here. 12 minus 3 is, what do we got? 9. 9z cube root of 2z squared. And that's it. You guys have the rest to do.